Section: Introduction. In this section, we explore the phenomenon known as grokking, which we recently discovered. Grokking occurs when a neural network initially memorizes the training data but struggles with test performance. After extended training, it suddenly achieves near-perfect generalization. Initially observed in transformer models working on modular arithmetic, we have seen grokking in other areas like group operations, sparse parity, and image classification. While grokking is fascinating, it adds unpredictability to training and reduces practical efficiency. When a model shows low training loss but poor validation performance, it becomes challenging to predict when it will generalize. Ideally, we want the model to improve steadily during training, minimizing the difference between training and validation errors. This leads us to ask how we can adjust training dynamics to ensure timely generalization. Our research indicates that data embedding is key to training dynamics, and effective embedding allows for continuous progress. To achieve this informative embedding without high computational costs, we introduce a new method that utilizes the embedding from a smaller, weaker model to speed up the generalization of a larger target model. Our method involves two main steps. First, we train a weaker model until it achieves decent test performance. Second, we extract the learned embedding from this weak model and use a linear mapping to initialize the target model's embedding before training it. We analyze this approach theoretically using a two-layer neural network on a high-dimensional XOR classification task where traditional training shows grokking. We demonstrate that our method allows the target model to generalize directly without delay. We also validate our method empirically on various algorithmic tasks that exhibit grokking, using both fully connected neural networks and transformers. Our results show that our method effectively eliminates grokking and enhances efficiency. In summary, we present a novel method that leverages embeddings from a smaller model to accelerate grokking in a target model. We provide theoretical justification in the context of an XOR classification task and empirically validate our approach across several algorithmic tasks that typically show grokking during standard training. Section Summary. In this section, we introduce the phenomenon of grokking, where a neural network initially memorizes training data but later achieves near-perfect generalization after prolonged training. We propose a novel method that utilizes embeddings from a weaker model to enhance the training dynamics of a target model, enabling continuous progress and effectively eliminating the delays associated with grokking. Section: Weak to strong knowledge transfer. In this section, we propose a method for transferring knowledge from a weaker model to a stronger one. We start by fine-tuning a small model, which acts as a teacher, to generate pseudo-labels for a larger student model. Interestingly, the student model can sometimes perform better than the teacher. We also introduce a learned linear growth operator that uses a linear mapping of the small model's weights to initialize the larger model's weights, speeding up the training process. Our approach specifically focuses on transferring the embedding layer from the weaker model to the target model, reshaping the training dynamics to enhance grokking. To illustrate the importance of data embedding in training dynamics, we analyze the modular addition task, where we compute the sum of two numbers modulo a prime number, specifically 113. Our dataset consists of pairs of integers and their corresponding sums. We randomly select 25% of this dataset for training and evaluate four types of embeddings. 1. One-hot embedding, where each integer is represented by a unique binary vector. 2. Binary embedding, where integers are encoded in binary format, padded to a specific length. 3. Fourier embedding, which uses trigonometric functions to represent integers. 4. GPT embedding, which utilizes a pre-trained model to encode integers. We find that one-hot and GPT embeddings show clear grokking behavior, while binary and Fourier embeddings demonstrate continuous generalization. Notably, Fourier embeddings allow for both memorization and generalization. We observe that general embeddings can lead to delays in generalization, while task-specific embeddings facilitate continuous generalization. Previous research indicated that a large initialization scale could cause generalization delays, and reducing this scale might accelerate grokking. However, our findings suggest that grokking can still occur even with careful tuning of the initialization scale, indicating that the kernel regime may not be the only factor influencing grokking. We also compare the empirical neural tangent kernel (NTK) changes across the different embeddings, finding similar patterns. Ultimately, the choice of embedding significantly affects training dynamics, and an informative embedding can bridge the gap between memorization and generalization. However, identifying such embeddings for specific tasks can be challenging. For instance, while binary embedding helps with modular addition, it does not work as well for modular multiplication. In the next section, we will demonstrate that creating a task-specific embedding from training data can effectively accelerate grokking, using a smaller, weaker model to learn this informative embedding. Section Summary. In this section, we propose a method that transfers the embedding layer from a weaker model to a larger target model to enhance training dynamics and accelerate grokking. We demonstrate that the choice of data embedding significantly influences training outcomes, with task-specific embeddings improving generalization and reducing delays compared to general embeddings. Section: Our method. In this section, we propose a straightforward and principled approach to speed up the grokking process in training neural networks. Specifically, for a given task and training set, we consider a target model that includes a trainable embedding layer. Our method unfolds in two main steps. First, we train a weaker model with a smaller embedding table on the training set until it achieves a reasonable performance on the validation set. This weaker model can be significantly smaller or even have a different architecture compared to the target model. By doing this, we aim to create an informative embedding that will assist in training the target model, which helps reduce the computational costs associated with obtaining this embedding. Next, we initialize the target model's embedding layer using the weaker model's embedding and a randomly initialized matrix. We train the target model with this combined embedding, which allows it to start generalizing quickly rather than just memorizing the training data. We also explore a specific case study involving XOR classification, where we analyze a dataset with both signal and noise features. The model needs to learn all features to generalize perfectly. We define a two-layer neural network and use gradient descent for training, observing that grokking occurs, with overfitting happening early on and generalization starting later. Our method aims to create a new embedding that eliminates this delay in generalization, which we will detail in the following sections. Section Summary. In this section, we propose a method to accelerate grokking in neural network training by first training a weaker model to create an informative embedding, which is then used to initialize the target model's embedding layer. This approach allows the target model to generalize more quickly, bypassing the initial memorization phase, as demonstrated through a case study on XOR cluster data. Section: Empirical Analysis of the Weaker Model. In this section, we conduct an empirical analysis of the weaker model. We begin by training a small two-layer neural network with just 3 neurons until it converges. We denote the first layer weight matrix as W, the number of training steps as T, and the trained model as F_S_T. Due to the complexity of the training process, it is challenging to derive a precise formula for F_S_T and W_T. We investigate what the model has learned and how effectively it performs. Our results show that this weak model achieves a test accuracy of about 75%. The neurons we visualize reveal specific patterns, and we note that the features learned are sensitive to how the model is initialized. However, we consistently find that the model learns 3 out of 4 specific features when the accuracy is around 75%. We recognize that an optimal function for this classification task requires 4 neurons to represent all features. Thus, it is intuitive that our weak model cannot generalize better with only 3 neurons. We formally establish a lemma regarding the expressive power of F_S, indicating that its performance is limited to a maximum accuracy of 75%. Although F_S_T does not generalize perfectly due to its limited capacity, it successfully identifies a subset of features after training. This allows us to create a high-quality embedding for any input in a lower dimensional space, which shows well-separated data points in 3 dimensions with a higher signal-to-noise ratio compared to the original embedding. Next, we examine the ratio between the norms of the complementary subnetwork and the generalizing subnetwork to estimate the signal-to-noise ratio of the distribution with the new embedding. The first 2 rows of W(T) correspond to the generalizing subnetwork. We define the norm ratio, which shows a proportional relationship to the noise level and the inverse of the square root of the number of samples. We also observe that as the training converges, the updates can be viewed as a weighted average of the input data. In the theoretical analysis of the target model, we consider it as a larger model with a specific structure. The embedding matrix U comes from the first layer weights learned by the weak model. We express the components of U in terms of orthogonal features and additional parameters. We make several assumptions regarding noise levels, initialization scales, and the number of neurons to ensure that the signal-to-noise ratio is sufficiently high for effective learning. We initialize the parameters and use gradient descent to update the linear layer of the target model. Our theorem states that after just one step of gradient descent, the target model can overfit the training data and achieve nearly perfect test accuracy. This result highlights that our method significantly enhances the generalization speed of the target model, bridging the gap between overfitting and generalization. We also note that the computational cost of training the weaker model is minimal compared to that of the larger target model, suggesting that our approach may reduce overall computational expenses. In the next section, we will compare the computational costs of our method with standard training procedures. Section Summary. In this section, we empirically analyze a small 2-layer neural network model, finding that it achieves around 75% test accuracy despite its limited capacity of 3 neurons, which restricts its generalization ability. We also establish that the learned features from this weak model can be effectively transferred to a larger model, allowing it to achieve near-perfect accuracy after just one step of gradient descent, thereby enhancing the overall computational efficiency of the training process. Section: Experiments. In this section, we empirically investigate modular addition and multiplication, along with the sparse parity task. Our experiments confirm that our approach effectively reshapes training dynamics and eliminates delayed generalization for both fully connected neural networks, FNN, and transformers, TF. We utilize the Atom W optimizer throughout this section. For the FNN, we start with a 3-layer model and focus on tasks like modular addition, modular multiplication, and the parity task. We compare these results to training a model from scratch. The modular addition task is defined as finding the sum of 2 numbers modulo a third number, while modular multiplication involves multiplying 2 numbers and taking the result modulo a third number. The parity task consists of a dataset where the output is the product of a subset of inputs, with specific parameters chosen for our experiments. For the modular tasks, we use a 2-layer neural network with a trainable embedding as a weak model, training it for 10,000 epochs. We then initialize the target model using the embedding learned by the weak model. Our findings show that our method nearly removes the sharp phase transition typically seen in standard training. We select all training hyperparameters through grid search, aiming for the configuration that achieves 99% test accuracy the fastest. We observe that fluctuations in accuracy are linked to the slingshot mechanism and instabilities from large learning rates, which we believe aid generalization, so we maintain our selection criteria. For the parity task, we employ a 3-layer FNN as the weak model, since evidence suggests that a 2-layer FNN without bias cannot generalize well. We train the weak model until it reaches 70% test accuracy, then transfer the first layer's weights to the target model. Our results indicate that while the weak model experiences a generalization delay, the larger model that inherits its embedding generalizes smoothly. To further explore the effectiveness of our approach, we conduct an ablation study by varying the training epochs of the weak model in the modular addition task. We extract embeddings at various epochs and apply them to the target model, training it for 10,000 epochs. We define the time gap as the difference between when the target model first achieves 95% training accuracy and when it first reaches 95% test accuracy. If the target model does not reach 95% accuracy, we set the time gap to 0. Our findings show a positive correlation between the test performance of the target model and the weak model, suggesting that a well-trained weak model is crucial for the target model to generalize effectively with minimal delay. For the transformers, we discover that embeddings from the weak FNN can also be transferred to a transformer model, even one comparable to GPT-2 small. This transfer still reduces the generalization delay of the target model. We select a transformer with 8 attention layers and specific embedding and MLP dimensions. The input consists of 2 tokens, and we extract embeddings when the weak model first reaches 30% test accuracy. Our results indicate that our method allows the target model to generalize much faster than training from scratch, although both methods face training instability due to large learning rates. In terms of computational cost, we measure wall clock time. The total time for training the weak model and the target model is significantly less than training the target model from scratch, making our approach approximately 5 times faster. We also compare our method to the Grok fast algorithm, which aims to speed up grokking. The time gap for our method is 46, while Grok fast has a time gap of 11:19, highlighting the efficiency of our approach.